Hello and welcome to the old Fliers. Aircraft are noisy. If you live near an airport, you will know that. Some manufacturers of jet engines market theirs as quiet through advanced technologies like the Pratt & Whitney geared turbofan and the GE9X, which use higher bypass ratios and larger fans to move more air at slower speeds, producing less noise. The question is, how much of a jet airliner's energy is dissipated by sound? Sound is the mechanical wave that transports energy through a medium via the vibration of particles. That takes energy. It seems that it is a surprisingly tiny amount of energy, almost negligible from an engineering perspective. For a modern high bypass turbofan engine on a jet airliner, during cruise, the energy lost directly as sound is on the order of 0.01 to 0.05% of the engine's total power output. Let's break down why this number is so small and where the vast majority of the energy actually goes. Looking at the total energy balance of a jet engine and how the chemical energy from the burning jet fuel is converted and lost in several major ways. Useful thrust power is about 25 to 40% of total energy. This is the energy that actually pushes the plane forward. It is the useful work output. The efficiency here is described by the overall thermal efficiency. Exhaust heat is about 60 to 75%, the single biggest loss. A huge amount of energy is carried away as heat in the hot exhaust gases leaving the engine. This is a fundamental limitation of heat engines as described by the Carnot efficiency. Parasitic losses is about 1 to 2%, which is the friction in bearings, gears if present, and the power needed to run fuel pumps, oil systems, and other accessories. Radiation and convection heat loss is about 1%, heat that radiates from the hot engine casing to the surrounding air. Sound and vibration about 0.1 to 0.5%. The energy that becomes the roar you hear on the ground and the noise during flight. Why is the sound energy so small? Even though a jet engine is incredibly loud, the energy contained in sound waves is minuscule compared to the thermal and kinetic energy of the exhaust. The decibel scale is logarithmic. Our perception of sound, loudness, works on a logarithmic scale, decibels. A sound that is 10 decibels louder has 10 times the acoustic power. A jet engine at 140 decibels is phenomenally loud to our ears, but in absolute terms, the acoustic power is still only a few tens of kilowatts. Compare the numbers. A large jet engine, like a GE90 on a Boeing 777, produces about 110,000 horsepower or 82,000 kilowatts of power at takeoff. The absolute acoustic power it radiates as sound is roughly 10 to 50 kilowatts. Doing the maths, this is equal to about 0.6% of the total energy is sound at the very noisiest point, which is takeoff. Once at cruising altitude, the engine is operating at a more efficient, steadier state. The noise emissions drop significantly relative to the thrust being produced, making the percentage loss even smaller, well below 0.05%. If the energy loss is so trivial, why do aerospace companies spend billions of dollars on noise reduction, e.g. chevrons on engine nacelles, advanced acoustic liners, etc.? The reasons are almost entirely social and regulatory, not based on energy recovery. Airports are surrounded by communities. Noise pollution is a major public health and political issue. International bodies like ICAO set increasingly strict noise standards for aircraft certification. An aircraft that is too loud cannot be sold. Noisy aircraft can be banned from operating at night or may be charged higher landing fees. Spending a few $1,000,000 per aircraft to reduce noise is not done to save a few kilowatts of energy, but to comply with regulations, maintain access to airports, and be a good neighbour. Conclusion: while the sound of a jet airliner is the most noticeable output to a human on the ground, it represents a tiny fraction of its energy expenditure, less than 1/20th of 1%. The real energy battle in aviation is fought against the massive heat loss in the exhaust, not the sound loss. The relentless pursuit of fuel efficiency focuses on improving turbine and propulsive efficiency to convert more of that fuel's energy into useful thrust, making the already negligible sound loss even less significant. Thank you for watching. Support for our channel is appreciated, as are comments. The Pugachev's Cobra, also known as the Cobra Maneuver or simply the Cobra, is a dramatic and demanding aerodynamic maneuver in which an aeroplane suddenly raises its nose to a very high angle of attack before dropping it back to level flight, all whilst maintaining a roughly constant altitude and heading. It looks like a fighter jet briefly mimicking the threatening hood of a Cobra. It begins with the aircraft pitching up violently, reaching angles between 90 and 120 degrees. At this point, the plane is flying tail first relative to its original direction. The maneuver is performed typically between 300 and 420 kilometers per hour. The aircraft loses a significant amount of speed during the pitch up as it acts like a gigantic air brake. The Cobra cannot be sustained as it is a dynamic, transient maneuver. The aircraft does not hold the high angle of attack position, but instead falls through it, returning to level flight. It is only possible with aircraft that have specific design features, primarily thrust vectoring and relaxed static stability. The maneuver was first demonstrated publicly by Soviet test pilot Viktor Pugachev at the 1989 Le Bourget Air Show in Paris. He performed it in the Sukhoi 27 Flanker, a highly agile air superiority fighter. Pugachev's public demonstration earned him the naming rights. The Cobra isn't just pulling back hard on the stick. It is a carefully controlled maneuver that exploits specific aircraft capabilities. Most aircraft are designed to be nose heavy and naturally return to level flight if you let go of the controls. This is positive stability. Fighter jets like the Sukhoi 27 are designed with relaxed or negative stability, meaning they are naturally unstable. This makes them more agile but requires a computer, fly-by-wire, to constantly make corrections. This instability is what allows the nose to be pitched up so violently and quickly. While the original Sukhoi 27 could perform it without thrust vectoring, modern versions like the Sukhoi 30 MKI, Sukhoi 35S and the F-22 Raptor use thrust vectoring, the ability to point the engine nozzle up or down to initiate and control the maneuver more effectively and recover from it more reliably. The pilot rapidly pulls the stick fully aft, pitching the nose up. At the peak of the maneuver, the aircraft is almost stalled. The pilot then pushes the stick forward and uses thrust vectoring, if available, to lower the nose back to the horizon before the aircraft loses too much altitude or enters an actual stall.